This question asks how many bonding molecular orbitals are present in the cyclopentadienyl cation shown below. So to answer this question, we need a frost circle. So whenever you draw a frost circle, you're going to orient the molecule so that a point is facing down. So let's go ahead and draw that. In the case of the cyclopentadienyl cation, we're going to have kind of one point at the very bottom of our frost circle. And then we'll have these points here that are going to be touching kind of the edge of the circle. So this is our frost circle for our molecule that we have here on this page. What I can do is draw a dotted line across the middle. And when we do that, we can see a little bit more clearly what orbitals are going to be bonding orbitals and which orbitals are going to be anti-bonding orbitals. So any orbital that's below our dotted line, which is representing the non-bonding line, is going to be a bonding orbital. And any orbital above the dotted line is going to be anti-bonding. So in this case, we have 1, 2, 3 bonding orbitals and 2 anti-bonding orbitals. So our question is specifically asking how many bonding molecular orbitals are present. So the answer in this case is going to be 3. We can take this question a little bit further if we want to. We can ask ourselves, is this molecule aromatic, non-aromatic, or anti-aromatic? So in order to do that, we can fill in the electrons, the pi electrons on our molecule and put them into the frost circle. So if we think about how many pi electrons we have, there are 2 in each pi bond. So we fill in the bottom, 1, 2. But when we get up here to this next level, the orbitals that I've labeled as 1 and 3 are degenerate or equal in energy. So we put 1 electron in each orbital. So when we look at this molecule, we can see right away that we have kind of 2 unpaired electrons, and that's destabilizing. So right off the bat, we can think about, the 2 key things that you have to have in order for a molecule to be aromatic or anti-aromatic. Number 1 is it has to be a fully enclosed ring that is conjugated and planar. Right, and our molecule does satisfy that. We do have a fully enclosed ring with completely overlapping p orbitals at each location. Right. The second question is where we have issue. You have to satisfy Huckel's rule. They must satisfy Huckel's rule. Okay, and that is that you have an odd number of electron pairs. And in this case, we do not. Okay, we have an even number of electron pairs. Okay, we have 2 here and 2 here. So that's 2 pairs of pi electrons. So this molecule is less than 6 atoms in its ring size. So we would classify this molecule as anti-aromatic because it can't change its shape to become non-aromatic.